Hi, in this video we'll be continuing our discussion on finding the volume of solids of revolution. And we're going to be talking about the shell method in this video. So as the disk method used disks or CDs to find the volume, the shell method uses cylinders or shells to find the volume. So what do we mean by cylinders or shells to find the volume? When we use the disk method, we broke it up into these little rings with a small thickness and then added up those rings. What we're going to be doing this time is we're going to be taking small cylinders of a thickness dy in our case, and we're going to be looking at the volume of these cylinders and adding those up. So we'll have, say, this cylinder, maybe another cylinder here, and when we add all of these cylinders up, we should get the volume, or rather, we will get the volume of the solid that we're looking for. So, in order to do this, we need to know what the volume of a cylinder is. So the volume of a cylinder is it's going to be essentially like taking a hula hoop and dragging it up. So we're going to need the circumference, which is 2 pi r, times this thickness. Right? And in our case, what is the thickness going to be? Well, if it's parallel to the x-axis, it's going to be dy, like in the example below. So rotating around the x-axis, we have a small thickness here that's going to be dy, because it goes along the y-axis. And if it's parallel to the y-axis, we'll be dealing with dx's. So the shell method is used for things that have really nasty x integrals, but fairly nice y integrals. So let's take a look at an example. And we'll start with the shell method. And in this case, but not all cases, we can actually use the disk method as well. And we'll compare it and we'll see that we'll get the same answer. So let's find the volume of the solid formed by rotating the region bounded by y equals the cube root of x, so this guy, x equals 8, so let's go ahead and draw x equals 8 in here somewhere. This looks good. And the x-axis, so this. And we're rotating it about the x-axis. So we could use the disk method in this particular case, but let's use the shell method to illustrate the concept here. So for the shell method, we're going to have to use dy because we're rotating parallel to the x-axis. Okay, and what region exactly are we rotating? We're rotating this highlighted yellow here. So what we're going to need to figure out these shells. So if we draw a shell here, we'll go around, and we'll go around, and we're going to have this representative cylinder. So our shell, the volume of it, is equal to 2 pi r h. So 2 pi is 2 pi. R, remember, is the distance from the axis of rotation to the cylinder. So our R is going to be from our point here, this red point, to that. So if we were to draw another cylinder, maybe in blue, we would have something more like this, where our radius would be the distance from this axis to the point on the cylinder. Okay, so what is that distance? Well, we're going from y equals 0 to y. So in our case, r is going to be y. So let's just go ahead and rewrite that in blue and white. So now what's h? H is the height of the cylinder. Okay, and the height of the cylinder is going to be the distance between the two ends, right? So it's going to be our upper function, or rightmost function, minus the left function, right? Because it goes from this 8 here to this cube root of x. So the height of our cylinder, h, is going to be 8 minus the cube root of x. 8, well, or it's 8 minus y. So, or my apologies, 8 minus x. So let's go ahead and write 8 minus x. Okay, why is it 8 minus x? Because as x increases along here, our cylinder stays at a distance 8 minus x away. But now we don't have things in terms of y, we have things in terms of x. So we know that the cube root of x is equal to y. But we're integrating in terms of y, so we need x as a function of y. So that tells us, by cubing both sides, x is equal to y cubed. So h is 8 minus y cubed. So let's plug all this in, and remember the volume is 2 pi rh times the thickness. And our thickness in this case is going to be dy. So plugging all this in, we have the integral from a to b. We still haven't found our bounds yet, but let's plug everything that we do know in. 2 pi, we can stick on the outside. R is going to just be y times the height of the cylinder, 8 minus y cubed, dy. So now we just have to find a and b. So let's look back at our graph here, and we know that a is our leftmost point and b is going to be our rightmost point of the region. So this point here is going to be where the cube root of x intersects the origin. So we're going to have the cube root of x, or y cubed, because remember we're integrating from y. So those were x ones, but we're going to need y ones. So we're integrating from here, this lower bound, to this upper bound. So we're going to have y cubed is going to have to intersect. So y cubed is equal to 0. Right, that's our lower bound, and y cubed, our upper bound, is 8. Or, yeah. So that tells us that y is equal to 0, and this tells us that y is equal to 2. Right, this is x equals 8. Okay, so now we're integrating from 0 to 2 of y, 8 minus y cubed, dy, and we'll stick that 2 pi on the outside. So we have 2 pi, integral from 0 to 2, 8y minus y to the 4th, dy, which is going to be 2 pi 4y squared minus y to the 5th over 5 from 0 to 2. Again, the 0 doesn't matter because when we plug it in, we get 0 out. So it's going to be 2 pi times 4 times 4, so 16, minus 32 over 5. Okay, so 16 times 5, remember that's 80, and 80 minus 32 is going to be 40. So 2 minus 0, that's 8. And then we borrow there, so we get 7. So 48 over 5. So we have 2 pi 48 over 5, or 96 pi over 5 is our volume. Now that was a lot of work, and we're going to see that the disk method is a lot less work. However, that doesn't take away the fact that the shell method is used a lot in situations where the disk method doesn't work. There might also be situations where the disk method is less viable to use. So let's go ahead and use the disk method to solve this. And then we'll give an example. We won't solve it, but we'll look at an example where the disk method kind of fails or is a lot harder to work with. So remember, the disk gives us pi, the integral of r squared. It's parallel to the x-axis, so we're going to be dealing with dx. Okay, our radius, if we draw a quick sketch, this is the cube root of x. The radius is the distance from the axis to the outside. So our radius is just going to be the cube root of x. So we have pi times the integral of the cube root of x squared dx. And our bounds are already given to us. They were 0 and they were 8. So we have pi, the integral from 0 to 8, of x to the 2/3 dx, or pi, we can integrate this now. That's going to be x to the 5/3 times 3/5 from 0 to 8. And when we do this, the zeros go away again, and we have pi 3 pi over 5 times 8 to the 5/3, which the cube root of 8 is 2, and 2 to the 5th is going to be 2 to the 5th, 2, 4, 8, 16, 32. So it's going to be 3 pi over 5 times 32, which is 96 pi over 5. And as you can see, we get the same answer with both situations. Now, let's do a quick discussion as to where we would really use the shell method and where it'd really be a big advantage. So say we had a graph like this, where we have this parabola, say that's x equals, what would that be, like maybe y minus 1 squared. And then we have y equals x, and we want to rotate this blue region about the x-axis. If we were to use the disk method, we would come into a problem right here. So if we were to use the disk method, we would have the same function on top and bottom. So we would have to split the function at this point, and we would have to integrate, let's say this intersection point is A, and well, let's call this B actually, and we'll call the left endpoint A, and we'll call the final point C. So if we were to use the disk method, we would have to integrate from A to B, and then we'd have to manipulate the parabola and then we would have to add the integral from b to c of the parabola minus the line. We'd have to manipulate the parabola into the upper and the lower portions. So that would be a lot more algebra to work with, whereas if we just use the shell method, we would have, what would that be, pi, parabola squared minus line squared. Now for the shell method, we would have 2 pi. The distance between the axis and any point is going to be y. And then 2 pi r, so this is our r. And then we'll have our h, which is just going to be the line minus the parabola dy. And the line is already given as one function. The parabola is already given as one function. Dy is dy. And all we would have to do is find the intersection points A and B, which wouldn't be that difficult compared to manipulating a parabola into its top and bottom halves, and then taking the top half, squaring it, taking the bottom half, squaring it, and subtracting them. That concludes finding the solids of the volume of solids of revolution. I hope that this has helped you. If you have any comments, concerns, or questions, please put them in the comments below. And as always,